All right, so this next result is actually going to be one that we're not going to fully explore using this principle of mathematical induction. Rather, we're going to look at a few different examples to see what's going on, and then I'll just kind of quickly state why it's true in general, maybe give just a little bit of justification about why it may be true for a general P. It goes beyond the scope of this course just a little bit to actually show all of the little nitty-gritty kind of generalizations of why it's true, but it does become a super important lemma as we move into Fermat's little theorem. And that's going to be the next result that we're going to look at, which actually does have a really nice proof that uses this principle of mathematical induction, as well as being one of these super important building blocks that makes RSA encryption true. So in this case, we're going to be looking at this kind of nice little lemma that actually has a kind of a fun little name as well. It's often referred to as the freshman's dream, and you'll actually see as we go through a couple little examples why that name comes to be. So in this case, what we're going to be doing is we're going to be looking at adding together two things, in this case call them x and y, and I'm going to be raising them up to some prime power. But then at the end of the day, I'm going to be reducing that expression modulo that prime as well. For example, if I look at, let's say, x plus y, and let's just square it. 2 is a really nice little small prime number, and it doesn't take a whole lot of work to actually go ahead and square this operator out. So in this case, if I take x plus y and I multiply it by an x plus y, well, if I do that full double distribution, I'm going to have an x squared. The two little middle pieces are both an xy, and I have 2 of them. So in this case, that middle part's going to become a 2xy, and then that very last part's going to become a y squared. So in this case, that's exactly what you do kind of back in algebra whenever you first learn how to square these little binomials out. You do this double distribution or FOIL or whatever you do when it comes to multiplying these things out. What's neat about this is that if you look at that middle term, you see that little 2 staring you right in the face. And that was exactly that 2 that I was raising this thing to a power of. Well, what's going to happen is that if I reduce this thing modulo 2, well, I know that any multiple of 2 is going to become a 0 in this mod 2 world. So in this case, x and y both happen to be integers, and they're multiplied by 2. So I know that that entire thing is going to be a multiple of 2. So in the reduction of mod 2 setting, that's going to become a 0. So all I'm left with then is that first term, which is an x squared, and that last term, which is a y squared. So you can see in this case that it's going to kick out just an x squared plus a y squared mod 2. If I push this idea just a little bit farther, if I look at, let's say, x plus y cubed, well, what would happen is that I have an x plus y multiplied by an x plus a y multiplied by another x plus a y. And if I do this giant multiplication, and maybe I'll practice a little bit here. Okay, x squared plus a 2xy plus a y squared. All right, distributing that x, I'm going to have an x cubed plus a 2x squared y plus an xy squared plus a yx squared plus a 2xy squared plus a y cubed. All right, x cubed. What do I got in the x squared variety? I have an x squared there, an x squared there, so I'm going to have 3 of those. At the end of the day, I'm going to have just the y squared parts, which I also have 3 of as well. And then I have, whoops, that's supposed to be a squared, and that gets my cube. Okay, so if I take this component of x plus y and I cube it, well, you can see along the way that I have these nice little 3's. So if I were to reduce this thing in a mod 3 setting, those 2 middle terms would also disappear because I know that, well, whatever that kind of quantity, that should be a square as well. Sorry, I just botched a bunch of that. Okay, so if I take these x times y's, multiply them by 3, that resulting thing is then going to be some nice multiple of 3. And I know in this mod 3 setting, all of those things are going to disappear. That is, these things are all going to become a 0 mod 3. So all I'm left with at the end of the day is simply going to be that first term, which is an x cubed, as well as that last term, which is a y cubed, and that's going to be done in this mod 3 setting, which is a nice little result. So you can see that this idea of taking x plus y squared, all that ends up happening is that you just have to square the x and you have to square the y. To look at x plus y cubed, well, what's going to happen is you're going to have the x cubed plus the y cubed. None of that extra kind of little middle bits. So the reason why this is often referred to as the freshman's dream is that first year students kind of forget some of their classic algebra tricks and they're like, oh, I know what x plus 5 or x plus y to the 5th, you're going to say, oh, this is just equal to x to the 5th plus y to the 5th. You're just going to bring those little 5's in there. And in general, that's not going to be true. But what this is saying is that if you do this reduction modulo 5, that result actually is true. All of those little middle bits, just like you saw in the 3 case and in the 2 case, all of those little middle pieces are actually going to disappear. So this notion of just bringing the 5 onto the x and 5 onto the y is not true in general, but if you do this reduction modulo 5, it is actually true. So as I mentioned, we're not going to go into the full kind of guts about why this result is actually true in general. So here's kind of the proof when n is equal to 3, that one that we just got done doing. The idea is that, oh, if you take x plus y and you cube it, you got this component and that component. They both have a 3. When you reduce those things modulo 3, they disappear. What ends up happening in general is you're going to be making use of what's referred to as the binomial theorem. The idea is that if you have something that looks like an x plus y raised to a pth power, you can always do this giant expansion. You have this kind of classic Pascal's triangle, and you have all of these really nice little coefficients that come into play. What's going to happen is that if I raise this thing up to the pth power, all of those little coefficients are always going to have a multiple of p floating around. So what's going to happen is that when I reduce this thing modulo p, that component, that component, that component, and that component, they're all going to disappear. They're all going to become zeros mod p, and all I'm going to be left with is an x to the p and a y to the p, which is exactly the result that I'm hoping to get. So like I said, I definitely am referring to this as a sketch of this proof. I'm kind of sloppy in this idea of why all of those things would actually become zeros mod p, but it's a nice little result that we can actually use, as I mentioned, in this next much bigger proof, this very important Fermat's little theorem, which is going to become a super important result as we move forward. So for now, it's just kind of a cute little result to see kind of all of these little pieces come into play, but it does have really important ramifications later.